the mic situation. Let's get started here. So anyway, welcome everybody, and thank you for staying in the kind of the humid, hot weather here. Just.
You want to smoke?
It's okay. I've already closed it. It's fine. Yeah. All right. Okay, I think it's better because we need to have a microphone that we can pass around. Otherwise, there wouldn't be a panel discussion. Anyway, welcome again. So the topic of the festival, in some sense, is neuroscience and Okay. Okay. So the general theme of the festival itself is sort of making the connection with, or at least talking about artificial intelligence and neuroscience. There are, of course, other scientific topics we're covering. So to continue with that theme, what today we want to actually discuss a little bit with some experts here is the idea of what is actually the relationship between one particular form of artificial intelligence, what's colloquially now called deep learning, and actually the way the brains work. So that sounds like, why would you even care about that? So I'm going to just ask those of you who have heard the term deep neural networks or deep learning in any one way, whether in stories, in your classes or whatever. Okay. So there are many of you who actually have not heard of the phrase deep learning. How many of you have heard of the word neuroscience? Okay, this is good. So of course it's the study of the brains. So deep learning is a particular form of, I would say, sort of data understanding, if you will, or data analysis, which is used to recognize patterns. When you now take, let's say, a photograph on almost all of your smartphones, right? You point at a scene, and most programs automatically highlight the face, right? I mean, because we think that when you take photographs, faces of humans are of interest. So you take images, and there is something in the phone that automatically picks out faces, right? There can be many ways in which an image can be understood, if you will, by the machine or decoded to recognize a face. And one way in which you can do is using something called a deep neural network or a convolutional net, right? So it's one particular way of automatically doing pattern recognition or image recognition, right? But that has now spread to not just image recognition, but also to sound analysis, sound recognition, to your consumer patterns, like how and what do you buy on Amazon, what movies you watch on Netflix or Hulu or whatever, and so on and so forth, all your habits, if you will. So at the heart of it, these are particular artificially intelligent, if you will. You can question whether they're intelligent, but they are artificially intelligent systems which take huge amounts of data and learn to recognize specific patterns that you are telling the program typically to recognize. There are, of course, now modern variations where you may not even have to tell it what to recognize, but it's sort of ways of sorting things and recognizing parts of it, right? So why would this have anything to do with brains, right? And that's a question I think the panel, we can discuss this, but one of the ideas is the very way in which the architecture of some of these so-called deep neural networks, these AI systems, that was somewhat inspired by how brains are organized, right? At least some animals' brains are organized. This has to do with, there's an input layer, and then you can have another layer of neurons which receives inputs from that front layer, does something, and then passes on to another layer. So you build these sort of hierarchical systems to, in the end, say, oh, what I send in the input is X or Y, a dog or a cat, right? So this kind of an organization seems to be apparent in many brains, particularly in the visual system of, let's say, humans and primates, right? So that was the inspiration for designing some of these deep neural networks. But then very soon that became a field on its own because the mathematics of it, of the computing of it, became extremely sophisticated, and computing power just in computers became enormous. Huge amounts of data came. So that has become its own field. So you can say, okay, here's something that was inspired by the brain, but there is now essentially a machine system. Why do we have to go back to say, okay, does it now work just like the brains work or not? Or do brains work like how these artificial systems work? That comes from the fact that when you study brains, it's very difficult to get very detailed analysis of lots of the components essentially in real time, or do lesions, do experiments. So you're kind of a little bit stuck with how you are actually looking at brain systems. We have a lot of technologies, but it's still limited. Whereas in computers, in machines, you can look at almost all of these things, right? So can we do that and then get some sort of inspiration from that? So that's a motivation. There are many other motivations, but that's where I'll stop with giving you the background, and then we can turn to basically the panel experts to ask what are the things that they think are reasonable to think about in terms of deep neural nets, deep learning systems, artificial ones, and the way, let's say, brains work. We won't specify whether it's human brains or animal brains, but how brains work, right? So let me maybe I'll start in some random order based on kind of the question that I want to sort of prompt the panelists. I want to first start by saying, is there something that's starkly different the way that deep neural nets work? Like, for example, the system that takes the image taken from your smartphone and quickly recognizes as a face or a human face or a non-human face, right? Some system. Is there something starkly different about how that works and how brains work, right? We're starting with something that's very different. So maybe I'll ask maybe the senior computer scientist in the panelist, Dr. Kambhampatti, to say, like, what do you think about that? So, yeah. No,
Is that good? Okay, thank you. So I should mention that this is a panel full of neuroscientists and somebody who understands both computer science and neuroscience. The only connection I have with neuroscience is I believe, a brain that possibly is working. Beyond that, I am not an expert in neuroscience. My stance on whether deep learning's connection to brains comes from my stance on where do techniques for artificial intelligence come from. Abraham Lincoln is said to have said that what I really want to do is preserve the Union. If I can preserve it with slavery intact, I will do that. If I can preserve it with half the slavery intact, I will do that. If I can preserve it while abolishing slavery, I will do that. The same thing for me about AI. As far as I'm concerned, all I'm interested in is able to get to human level intelligent behavior. If I can do it with deep learning, I'm fine with doing it. If I can do it without it, I'm fine with doing it. And if, in fact, there's a combination that I'm also fine with doing. And in particular, I believe that we may very well wind up needing combination. The question that was posed as to, are the deep neural networks different from brain? In a different meeting, somebody pointed out, and I'll just channel it to you, that was a neuroscientist, that the connection between neural networks and the brain is the word neural. That's it, okay? In fact, there's just the current day neural networks are so different in many, many ways from the way brain works. In particular, one of these startling statistics is to get something at the size of brain, and a neural network of the size of brain, it would require the power consumption of the New York City. Whereas our brain, thankfully, doesn't require the power consumption of New York City. Otherwise, we would be shutting off pretty much every few seconds. So I think we've been inspired to some extent, especially in tacit learning tasks, if those of you who have heard my other talk, where we have no theories. We basically thought we had some theories of computer vision. They were bogus. They were theories of computer speech. The speech recognition, they turned out to be bogus. The best was let the system find patterns the way whatever it wants to do, the way we had to do. Their deep learning methods are pretty much the primacy. They have been quite well organized. But much of the civilization is a human intelligence is a marvelous interplay of this tacit knowledge and explicit knowledge. And I'm not at all clear as to how to combine those sort of what turns out to be symbolic knowledge that we get to be able to exchange with each other with the sort of perceptual techniques for which deep learning apparently is working well. I'm not sure whether I came anywhere close to what you wanted me to answer.
I think that just to paraphrase, I think the idea of kind of taking this, what you call tacit knowledge or common sense knowledge, to sort of build that into the system seems to be a very big kind of a difference.
No.
Yeah.
Yeah.
Yep. Right. So I don't know if the other panelists perhaps want to add something to it. I mean, the conversation, we're going to just sort of freely talk about very different things. So I feel like we can start with all of these differences from hearing from all the panelists, and then we can move on to other things. Yeah.
Yeah, just to reinforce what both Venki and Rao said, the model for a neuron that is used in deep learning right now goes back to the 1940s. So it's sort of, neuroscience has pretty much left all that behind, but people in AI are still using that 1940s McCullough-Pitts model of a neuron, of weighted sum followed by nonlinearity. So that's one major difference I would point right away with what's happening in computational neuroscience and what people use in AI. The second is the architecture, right? So traditional deep learning, you have these sort of bucket brigade architecture, which is you have some processing, pass on the bucket to the next, and then you have that all the way till, you can have it very deep, 20, 30, 100 layers, but still is this feed-forward architecture, whereas in the brain, it's highly, feedback-based. It's recurrent locally as well as globally. And in some sense, it fits with this notion of a Bayesian brain or a predictive coding type of brain where you're saying the brain is always doing this hypothesis testing, right? So many times you probably had this sensation that you're anticipating something. The thing that grabs your attention are the surprises, the novelty, right? So the brain is driven by novelty because that's how you learn, right? So you're actually always constantly trying to anticipate what might happen, and then the surprises are what drives both your attention as well as your learning. So that's something that has not come yet to deep learning, but I think people are working on certain architectures, there's a PRID-net and so on, but that's a very fundamental difference. And lastly, I'll also mention, of course, there's the whole area of reinforcement learning, which is more of inspired also by how animals learn, but using rewards and punishments. And that's in the traditional deep learning, it's just using an optimization of an error function, which is not really the same as trying to optimize some kind of utility function or reward function. So I think we're starting to see some of that also being adopted by the deep learning community, but I think there's still lots and lots of really interesting ideas. So thank you all for coming, and I think there's a lot of potential there for people here in the audience to actually apply some of the insights from neuroscience to really deepen deep learning. Thank you.
Hello. So my take on this is a little different, and probably because I come from a mixture of fields. I started out as a physicist, went on to study birdsong learning, then got into language and neuroimaging. And I always thought that the sign of intelligence was to find ways to reduce my own work. Okay? And so I'm amazed as to why we would want to build artificial intelligence. Instead, we would want to build machines or deep learning to try and understand the brain. So my biggest interest in trying to look at these algorithms is to find ways as to how they can help me understand the data that I acquire during the different learning paradigms that we test, the brain data that we collect, and how that might inform us about how the brain works. So, and especially because I work on cognition, where I look at music, I look at emotion, I look at language, which are all sort of meta abilities. I think deep learning and artificial intelligence, if there might be such a case, is still far away from that. But suffice it to say, I have used deep learning methods very successfully to inform me about my data, and I find that its biggest promise, at least in the next couple of years.
Okay, so since I'm last, I obviously have to take a contrarian view. So let me start with this idea that there's a number of problems which for all of recorded history, the brain was sort of the only existence proof that there's a way to solve them. And this is the whole range of quote-unquote human abilities, of speech, of being able to recognize people, this whole range of things. And in the early days of computer science, it turned out that these were actually much harder problems than people had originally thought they might be. There were lots of inflated expectations of the early wave of artificial intelligence, which didn't work. So to me, it's actually extraordinarily interesting that after all the thousands of years of there being only one existence proof of a solution to these problems, we are now in a time when for certain very specific focused problems, there are two existence proofs, the humans and the machines. So I think that is very interesting and for a neuroscientist very suggestive, because now, as neuroscientists like to say, we have another model system. We have another subject on which to play around with, test our assumptions, see if there are any deep commonalities. And you know, I totally take the point that if we were to do a brute force way of trying to simulate every single neuron in the brain, this would be a disaster in terms of global warming. But, but let's ask the question the other way. What is the brain doing that allows it to perform computations which the computer struggles with, which the standard electronic hardware struggles with? And this is where I think that there's some possible insights and maybe even some possible parallels with computations that are happening at a very, very fine and energy efficient scale in our heads. And so I'm going to, of course, plug my favorite theme, which is to say that subcellular computations at the level of molecules, at the level of small electrical, subcellular signals and molecular signals, I think that there's some, I won't say parallels, but there's some resemblances, family resemblances maybe, with, say, McCulloch-Fix neurons or other staples, LSTMs, if you like, of deep learning networks. And so, you know, you don't have to have an exact one-to-one match in order to accomplish major computations. So I would like to make the suggestion that the brain actually implements in its, not in its superficial neuron level hardware, but in its very subcellular hardware and wetware, as they say, it implements a lot of the computations with incredible efficiency, and that this might be an interesting point to look for similarities.
That's great. So actually, I was going to prompt now further discussion somewhat based on what Upi just said, which is that so many people, I think when they switch from, let's say, being from a computer scientist or a physicist to a neuroscientist or somewhat something different, we always sort of are happy with metaphors, like something sort of looks like this, I can kind of think about it, this looks like a network. And I think one of the themes that I think excites a lot of people, it certainly excited me when I switched to neuroscience, which is that there seems to be this idea that you can separate hardware from software. So you know, you have this is something that really is the network, and then you can then build algorithms, build software, build tricks on that, right? So taking off Upi's point, so in the extreme, it might be there are two examples, you say. Is it possible that, let's say there's image recognition, that the software may have some sort of similarities, but the hardware is evidently very different. We're made of, you know, blood, sweat, and gore, and all that crap, but machines are in a silicon and, you know, silicon-based, right? Physical materials-based, not biological materials. So my question is that how much of this real separation that you can really have a hardware and the software, and they're two separate things, and then you can sort of understand one more or less ignoring the other or independent of the other. So I want to start by asking, maybe we'll start with Upi going in reverse since we sort of brought it up. So do you think that's actually a hopeful or a useful approach?
Yeah, I mean, I think that's a very nice line of separation, if you like, between the two approaches. So the way I look at it is, you know, all of us pay our homage to Mar, but Mar said that you need to separate the different levels of computation, hardware, software implementation, and so on, algorithm. So I would argue this, that through evolution, the solutions that nature has come up with are these incredibly energy and space efficient solutions. But it is through the abstractions, through the algorithmic level, if you like, that's where one can see parallels with what computers are doing horribly inefficiently, horribly expensively. So I don't think that you need to insist that the software and the hardware are interlinked. But I think that if you want to do it really, really, really efficiently, you probably end up somewhere down that route.
So if I may add there, Upi, would you think that if I was to understand the statistics of what's happening around me and try and draw from those rules, which are things that the brain...
Sorry,
which are ways that the brain might be processing information to draw those abstract rules. Applying those back when developing algorithms might turn out to be more useful?
There's always something to learn, but let me put it this way. You can, if you really struggle, you can implement, I don't know, a simple logic gate with chemicals. You can implement a McCulloch neuron with a real neuron. And that's absolutely an incredibly dumbed down way of utilizing the capabilities of the biology. So although you could do that, I don't think that's certainly not the way the optimized evolution and all of that would have ended up with a solution.
So once again, I would take an engineering view about how to get artificially intelligent systems during my lifetime, hopefully, maybe at least also some of the younger guys' lifetimes. And it is indeed true that nature's solutions to many of these things are amazingly efficient. If you think about flight, birds have amazingly efficient flight. There is a hummingbird that comes to my house all the time, lots of them. They do much better. They don't increase global warming one bit. If we had hung around trying to do mechanical flight the way birds do, we won't be having this panel, because none of us would have been able to fly to this place. I don't know if you saw, anytime on the flight, if you see the plane flapping its wings, get off like very quickly, because it's not going to work. So my point is, in the end, it may well be that now finally we are coming to a point where we have micro flights with flapping wings and so on that are indeed energy efficient, but that was much later than the time when Wright brothers had to take a decision on which direction to go. I believe this is the same sort of an issue with the learning, that the human taking imitation from humans for AI, in the sense that the biological intelligence, because we know so little yet about how biological intelligence works. I mean, I know I have amazingly great panelists here, but again, the last time I was in an audience member in a neuroscience panel, the guy basically said something to the effect that we are in the first inch of a 1 mile long trek in terms of our understanding of how brains work. So I could just wait and say, these guys will figure out how brains work, and then we'll implement it. That would be, at least from an engineering perspective, pretty bad. From a scientific perspective, it's very interesting to understand how my brain works. But from an engineering perspective, I don't see why computers have to think the same specific hardware way I do. But there is a related point, which is, however, that whatever the computers wind up doing, I should be able to understand, I should be able to interpret. And I have this longer point that I would like to make, that in some sense, if you let intelligences evolve independently of us, then don't complain that you can't interpret what those systems are doing. In a sense, I have an example that Gmail tells you some of the mails are spam. Many a time, Gmail has put in spam replies to an original mail that I had sent. So I send you an email, you send a response back, Gmail says this is spam mail. How dare it? Any response to my mail definitely is not a spam mail, but it's extremely hard to change the architecture such that that fact is actually understood at a hardware level by the system. It's so much simpler to give a rule saying replies to messages originating from you are not spam. So again, it's possible that you can have task-specific architectures that you can evolve over deep time. That's what we did. And we can speed up deep time. But I still think I don't have as much time, and so I would like to actually try to see approaches that may not necessarily be very efficient. They might actually increase global warming. But remember, one computer learns, all computers have learned. One of you learn how to swim, the rest of you still sink like stones. But one computer learns to do language, all computers learn to do language because they have USB connectors, which we are unfortunately missing. And so efficiency is not as huge an issue because of that direction. This doesn't take away from the fact that from a neuroscience perspective, I would, it would be great to understand how human brain works. And then, and if AI can help with that, that's fine. But if I really want to do just AI, I don't particularly care.
Yeah. So, yeah, just to go back to the original questions, like about the hardware and the software, please.
Yeah, I think it's a very important question that I've actually pondered a lot about in terms of, I've done both computer sciences for my PhD, computer vision, and computational neuroscience with Terry Sarnowski for my postdoc. And I think it's a very important question that we ask all the time, both in people doing deep learning as well as people in neuroscience, computational neuroscience, trying to understand the brain. And so I think it's important to know that we're actually in this particular lawn that's called Hodgkin-Huxley lawn. How many of you know who Hodgkin-Huxley, who they are?
I know that.
Very few, right? So it's one of the prime examples of computational neuroscience, being really making a breakthrough, right? So they were actually able to describe how a single neuron is able to fire a spike on action potential using mathematical equations or differential equations. These coupled differential equations were able to describe really how the physiology works. So it's a very interesting example of how mathematics was used to explain this phenomenon as a physical phenomenon. And they actually got the Nobel Prize for that particular description, the experiments they did with the squid axon and also being able to describe it mathematically. Now, if you look at that and you say, okay, why didn't the people in AI use that model, the differential equations model, to do their artificial neural networks, right? Any idea why not use that Nobel Prize winning differential equations, right? So that, one answer is, maybe you don't need that level of detail to get the kind of computation you get. So now you're going to the computation level where you have a network that you're simulating. So if you're really simulating at the detail of those action potentials and differential equations, it becomes very difficult to simulate a very large network, right? So the question then is, can you abstract away the principles that are important? So I think that's the key in this game here, is to abstract the computational principles from neuroscience so that we can apply it to artificial systems. And I think the current neural networks are a good example, but they're a little outdated. They're from the 1940s, but still they've really done excellent, right? As you can see, all the advances we had over the last 5 to 10 years are based on a very simplified model, which is a computation level description. But in fact, it misses a lot of the important details. So the question for us is, what are those new details that have come since the 1940s that are important for deep learning, right? So what are those new details in both the description of a single neuron, the synapses, computation being done in the connections between them, as well as the architecture, and how do you actually use those insights from neuroscience to then build a new artificial architecture? So I think that's the key problem right now.
Yeah. Do you have any follow-up thing, or should we move on to, yeah, so I think so just to prompt, so one of the other counterexamples given to sort of say like what deep learning or deep neural networks are doing very differently from, let's say, animal brains, is this idea of training sets. So for many of you probably know, in order to train a network, simple or complex, to recognize, let's say, just dog versus cat, to give you lots of images, right? I think the typical number of examples of dogs and cats that this network has to be trained on from scratch, when you have random weights to begin with, to train on, is in the thousands, if not hundreds of thousands. So, okay, if not hundreds of thousands, right? Yeah.
Thousands of millions.
Thousands of millions. Okay, it's a very large. I'm trying to be generous, right? It's very, very large, right? Too. But I think the general feeling is that for animal behavior, human behavior, we all get this feeling that very small number of examples are sufficient to kind of learn many things. Right? So that seems to be a difference that's pointed out. The idea that these networks are designed to have a huge amount of training and then they get very good, whereas natural intelligence, we seem to be able to get very small number of examples and get most of the way. Maybe we're not as good as a computer now doing dog and cat, but we're getting kind of pretty close. So I'm just curious to hear from the panelists, what do you think of this? Is there a real difference? Is there other explanations for this? I don't know, just to mix things up, maybe I'll ask Nandini to have a go at it first, if you wish.
So I think in the morning today, you showed a picture of an image generated by a computer, which was not a real human being. And but when people were asked from the audience, we couldn't really tell which was the real human being and which was the generated human face. Okay? And my first question that came up was, when people did these, did they ever follow up with functional imaging experiments to see if humans were shown these faces? Could they tell those differences apart in the scanner? No.
This was meant for humans, and humans are pretty bad in doing this. So there's a website which there, and I think we can't really tell. I mean, we are in the situation of Charlie Chaplin taking part in the Charlie Chaplin lookalike contest and coming in second. That's what we have become, essentially.
So clearly we've been able to, these algorithms have been able to make this jump where they've been able to extract out features which are able to give rise to human-like images, which we can't differentiate. So I think in that sense, I'm curious to try and understand that if there are features that humans use to try and distinguish images, for example, context, familiarity, or novelty, are these features part of algorithms is what my immediate question to the deep learning algorithm people would be. What can I take away from this which can lead to my understanding of how facial recognition is happening?
Go back to the training sets, right?
Okay. Well, just to throw in a little plug here, I mean, this question that Nandini asked about what can we learn from deep learning that is applicable to neuroscience, there's a whole field called artiphysiology, which is artiphysiology, yes, that's the real word. And then the idea is you basically perform the same experiments you would perform on an animal brain or a human brain on the deep neural network. And then you see, okay, can you learn about how this neuron, this artificial neuron is responding to this very complex face image or some other image. And so the idea is you then get some insights about biological brains by understanding, these artificial neural networks. So that's an interesting application. Maybe that would be helpful also for other areas. But I guess the broader picture there in terms of, where Venki said, humans learn from very few examples. There's also a little bit of a debate going on in the, I guess, the general AI computational neuroscience field of the Bayesian folks who think that there's a lot of information, prior knowledge in the brain that is developed over a long period of time, which is used for learning from very few examples. So there's a very, if you know about Bayes' theorem, you have some prior probability, you multiply it with your likelihood, you get a posterior probability, which is basically what you believe in terms of, what you just saw. So you're always interpreting what you just saw or what you heard based on your prior knowledge, which has been learned and genetically you've inherited it and so on. So basically, that is something that really explains a lot of human data from a psychophysics or behavioral point of view, but we still don't know if the brain actually implements it. So that's one of the big open questions in computational neuroscience is, does the brain somehow do probabilistic computation where it is keeping track of these sort of Bayesian statistics and so on? And if so, then it's doing it using these neurons. So how is that really happening? I think in AI, we're starting to see some of that also happening now, the implementation of probabilistic algorithms using stochastic neurons and so on, and including the generative models that were used for the deep fakes, right? They're actually stochastic neural networks that are generating these fake images. So I think there is some convergence happening, and it'll be interesting to see how it develops.
Right. So I don't know, Upi, if you have some thoughts, since we have a kind of coming to a close of our discussion to give you some time for the questions for them, right? There were a couple of questions for them. So any last thoughts on this?
Yeah, no, I think that this is, to my mind, one of the couple of really big questions in both fields. One is, I mean, to me also as a, purely with my neuroscientist hat on, it is an extremely interesting and difficult problem. How does one learn such complicated concepts in one or two trials frequently? That's, I think, a fundamental one. And the related concept, which was just alluded to, what is the prior knowledge? Or to pose it provocatively maybe, how does this relate to what's called artificial general intelligence? How can you use information from other domains to help in a new domain? I think these are crucial and very closely linked questions.
Yeah, I think we were supposed to sort of have a quick...
So on the I think sample complexity, which is the number of samples you need to recognize a particular concept, is a crucial problem right now facing all machine learning techniques. Human learning is very much sample complexity efficient, and the part of it is because we actually come to it with prior knowledge. So some of it, I mean, if you're coming from a brain level, then it's this question of how is the prior knowledge actually encoded. But in many cases, when you're trying to understand something new, you build on top of some symbolic understanding of the knowledge that you have up until then. Currently, we only have a very poor person's approach to having prior knowledge in neural networks, which is essentially these truncated networks, and that just is not scalable. So we really do have to have a flexible way of bringing prior knowledge into the learning process. Within the engineering side of AI, there has been, of course, there's been the symbolic AI techniques and the deep learning techniques that have come, and people have been talking about how to potentially marry them. In the context of course, neuroscience, how brain does it, I think these guys have much better idea.
Right. Great. So I think let's just thank the panelists quickly before I take maybe one or two very quick questions. So I think we're supposed to encourage audience participation, and we kind of went over time. So I think if you have a couple of people have some very specific questions, I'm very happy you can just yell out to me and I can repeat the questions on the mic. No questions? I think he has a microphone, so.
Just would like to know whether the bionic limbs, which are right now in market, so whether are they fit under neurophysical?
I didn't get the first part of your question.
Bionic limbs, artificial limbs.
Artificial limbs? I think that's probably well outside the scope of what we're discussing, so I think maybe it's a different question. So, yeah.
Yeah, just to quickly say, I mean, many of them are either not controlled or controlled by muscle signals, but not brain signals.
Not from the brain, yes. Yeah. So that's why it's not quite a neural thing yet, yes.
As sir mentioned about the wet memory system or using fluids for storage as a storage device, I'd like to ask that how far have we come in considering using a fluid state of memory device, and is it really, I mean, promising to do the invention in that direction?
What state of memory you're talking about?
Using fluids for storage.
Fluid storage? I'm not sure.
Like using chemicals as storage medium.
I don't think there's any particular industrial application of that. It's the end product of a couple of billion years of evolution.
Yeah, I've seen a post about IBM's latest invention. They have, successfully moved the position of a single molecule. So, if we consider that kind of technology for storage,
I think these are very good questions, obviously, but I think it's probably very unrelated to what we're discussing. So I don't think we can quite answer that. We're not the people to answer that question for you. So sorry. Yeah, I think we should probably stop there.
Yeah. So in the interest of time, I think we can't take any more questions for now. So everyone who is here, there's a lucky draw for people to register on a link that I'm about to say. Guys, please go there and register yourself for this lucky draw, okay? indiasciencefest.org/I am here. IAMHERE. Right? indiasciencefest.org/IAMHERE. I'll give you guys a few minutes to do that.